All right, welcome everyone to 13.9, or 13.9 is really the section that I've kind of named this in these notes just because it comes right after 13, but it's not quite 14 yet. In reality, if you were looking for this content in our course textbook, it exists in 15.8, which is about cylindrical coordinates, 15.9, which is about spherical coordinates, and then a little bit in 16.6, which is about the parametric surfaces. So that's kind of where this lives. It does also very naturally fit where we're putting it here. It is kind of a direct upgrade of other coordinate systems, and in particular, parametric curves that we've been dealing with a lot in chapter 13. We're going to be dealing with parametric surfaces. And so we're going to find different ways to parameterize surfaces rather than maybe the classic X, Y, Z's that we've seen previously. So I want to tell you a little about these coordinate systems. So first of all, we're going to talk a little bit about cylindrical coordinates, cylindrical coordinates, which is basically an upgrade of polar coordinates. So right now, maybe look around here, right? Polar coordinates in two-dimensional space, right? We're going to expand these to a third-dimensional space. And one reasonable way to do this is going to give us cylindrical coordinates. So cylindrical coordinates here, if we have some point P in space, then we can describe this as an ordered triple where we have r, theta, z, in which the r and the theta are going to be the polar coordinates. So remember polar coordinates back from calculus 2. And this is if you were to take that point and kind of project it into the XY plane, you would use that same R and theta there. So polar coordinates for the vertical projection. Into the XY plane. Remember, that's the same as z equals 0. And then z is just the same z that we know and love from rectangular coordinates. So z is going to be the rectangular vertical coordinate. So I find that this picture here really helps with this. So if we were to take a point in space, right, P here, and project it down into the XY plane, well, remember in the XY plane, we already know a coordinate system called polar coordinates, right? In which case theta comes off that positive x-axis in this counterclockwise direction. So if you kind of turn your head, right, and look at this, imagine if it was a paper sitting on your desk or something like this, right? Theta is in this counterclockwise direction away from the positive x-axis, and r is this distance that we're going away from the origin in the XY plane. And then this z coordinate, right, is the same z coordinate from a rectangular coordinate system, right? So it's that height. How much do you go away from the XY plane? So that being said, we can come up with the conversion equations from Cartesian to cylindrical because they're darn near similar, or essentially the same as the transformation equations from polar into Cartesian and vice versa. So in this case, right, x is going to be equal to r cosine theta, y is going to be r sine theta, z is just going to be z, right? Z makes perfectly fine sense in cylindrical. X squared plus y squared will indeed equal r squared. And finally, this one you may not remember from polar coordinates, but if you go back to your Calc 2 stuff and revisit, you do get this one, y divided by x is equal to tangent of theta. And let me just say that is exactly if you were to use these equations right here. So if we use these equations, we'd have y is r sine theta, x is r cosine theta. You'll notice that these r's perfectly cancel out, and then you'll have sine divided by cosine, which is exactly tangent of theta, right? So this one ends up being very useful if you're transforming from cylindrical or polar into Cartesian, right? If you have a theta value and you're interested in the x and y value, you can help with this a little bit. Okay, so let's go ahead and use these really quick and solve a few problems. We have, first of all, In Cartesian coordinates, x, y, z is equal to -1, 1, 1. We'd like to transform this into cylindrical coordinates. So, okay, well, there's a couple of ways that we can go about this. But again, we're going to be trying to figure out an r, a theta, and a z. So one of these we've already won, right? We know that z is supposed to be equal to 1. And so we have 1/3 of this completed. In order to figure out r, for instance, we can use r squared is supposed to be x squared plus y squared. And so if we go ahead and put in our x and we square it, so -1 squared will be 1, and our y, 1, we square that, we're going to get 1. Add those together, that's going to give us that r squared is equal to 2, or that r is going to be equal to √2. Now, you may remember from your calculus 2 days, right, that this can be either a positive radius or a negative radius, and either one of those can make sense and is, legitimate. In this case, in calculus 3, we're going to be restricting down to just positive radiuses because we can do everything that we need to with positive radiuses. Excuse me. And if you introduce negative radiuses as well, although that is fine, you do have to kind of be careful and need to exclude these here and there. So we're going to stick with just positive radiuses. And that's why I just did positive square root of 2 rather than plus and minus there. Okay. And then notice we're going to go ahead and use this one right here. We have a y and an x. So my y is 1. My x is -1. And when I divide those according to this equation, I'm supposed to get tangent of theta. So in this case, we have -1 is equal to tangent of theta. And so we need to know, okay, when is a value, what is the value of theta, where we get -1. And so, okay, may want to pause or think a little bit about your unit circle here. And I find if we draw a quick picture of this, remember tangent is like the slope, right? It is literally this y divided by x, the rise divided by the run that we see up here. Right? And so we want the slope to be -1. So something like this. So some line going through the origin with a slope of -1. What theta values make this true? And in this case, we're going to go ahead and choose a theta value of 3 pi over 4. Right? So here would be 1 pi over 4, 2 pi over 4, aka pi over 2, and then 3 pi over 4 gives us this point right here. And then we could talk about, again, kind of their same thing when we were dealing this in polar coordinates, right? There are multiple correct solutions. So again, we're going to be kind of dealing with this, ideally in the arena of 0 to pi really is the best case. But quite often, if you're given this like in a web work problem or something like this, they give you some bounds. And so you know that this is the correct one to choose rather than the -pi over 4, or that would also be equivalent to 7 pi over 4. Okay. So that is changing from Cartesian into cylindrical. I guess I could write down my final answer, right? R was equal to √2, theta was equal to 3 pi over 4, and z was just equal to z, which was 1. So here, right, would be my final answer. One more problem. Go ahead and try this one on your own. Pause the video, and then we'll go over the results together. All right, so hopefully I've given you enough time. Here is my result. Notice that I wasn't super creative with this example, right? I had that my r was √2. I had that my theta was 3 pi over 4, which happened to be the same results as the one up above, or the same kind of conditions that we had up above. But notice that in order to get there, right, we had to use very different equations. So that's why we kind of have all of these. Notice that again, when we were converting from Cartesian into cylindrical, we were using these two right here. However, when we were converting from cylindrical into Cartesian, we were using these two right here. So again, if we needed an x and a y and we already have r's and thetas, right, we can very easily plug those in to r cosine theta and r sine theta, and that's going to give us the result of -1 and 1 respectively. And then of course z is just equal to z. In this case, I changed the z to 2, but okay, -1, 1, 2. Okay, so that right there is an introduction very quickly into cylindrical coordinates. Of course, we will be dealing with this substantially more, in class. And as we transition into chapter 15, we will be integrating eventually in cylindrical coordinates. Okay, the last bit here, right, is that we're going to be talking about spherical coordinates, right? So if I imagine a little bit that, we have some archer or some turret or something like this, right? Some stationary thing that is shooting projectiles, right? Baseballs, what have you, right? You need to tell it a few things in order to ideally hit your target. You need to say, right, how hard should you fire the projectile? Where should we aim left and right, right? Usually there's some rotation like this. And then also, where should we be looking up and down? Those three parameters or those three variables are the exact parameters or variables in spherical coordinates. So in spherical coordinates, right, how hard you should fire the projectile. This is, with a fancy math speak, would be the magnitude of our vector. Where should we aim left and right? Well, rotation about that z-axis, right? If we go back up to our cylindrical stuff, right? Where do we aim left and right? That had to deal with this theta value. So it's actually the same theta value from cylindrical or polar coordinates. And then finally, where should we aim up and down? Well, this is usually denoted as phi. This is also pronounced phi. So you can either say phi or phi. I'm not even sure which one I'll say necessarily more in class. Probably phi. Phi's, I believe, a little bit more American. So I'll probably say phi. It's kind of like the same thing, right? Pi can also be pronounced p. So p or pi. It's the same thing, phi or phi. So anyway, I'll probably be saying phi. So this is, again, where you're looking up and down, right? And so 0, if you have a phi value of 0, you're looking straight up. If you have a phi value of pi over 2, you're looking straight out. And then if you have a phi value of pi, right, you're looking straight down. So this picture, again, right here is very useful in kind of seeing what's going on. So again, this rho value, which is a little bit like r, it's like a 3-dimensional radius, right? It's how far the point is away from the origin in the 3-dimensional case. So that right there is our rho. Our theta value is the same theta value, telling us how much do we turn left and right. And then finally, the phi value there, phi is telling us how much do we look up and down. So it may start off at 0 at the positive z-axis, and then the larger and larger the phi value gets, you start looking eventually horizontal, and then you keep that going, and you'll end up being negative as well. All right, so one more picture that I think is very useful here is if I kind of take this and I look at it straight on here, this will help us develop some of these coordinates that we're about to, right, or equations that we're going to need in order to transform between well, cylindrical to spherical and even Cartesian to spherical. So if I kind of think about, here is my point P. Again, I've just kind of turned this rectangle a little bit on us, right? So this right here is R, and this right here is rho. Still kind of, and maybe I could color coordinate these things a little bit, and that would help. So that'll be that. I'll use black here for R down here, right? And this straight up and down value, remember that straight up and down value is the Z value of the point, how much we've gone up and down. And then if we were to have kind of this imaginary bit right here, right, this is like the positive Z axis. And this right here would be the phi value, right, or the phi value, how much we've rotated off of that positive Z axis. And you may remember from your good old geometry days, right, whatever that value is there, that is going to be the same value right here. So now, oops, we have this beautiful right triangle with, the side lengths marked rho, Z, and R, right? And of course we have this angle phi. So we can go ahead and come up with, because we have formulas for right triangles, sines and cosines and tangents and all that sort of stuff, some good ways to transform between these. So in particular, if I was to set up, right, sine of phi, right? Sine of phi, well, sine of phi is supposed to be the opposite over the hypotenuse. So the opposite well, opposite of phi is going to be r, divided by the hypotenuse, that's going to be rho. So in particular here, we can write that r is supposed to be equal to rho sine phi. And then also, if we were to write down an equation for cosine, so cosine of phi, well, cosine is supposed to be adjacent over hypotenuse. So adjacent to phi is z, and the hypotenuse is still rho. And if we were to rearrange these, we would get z is equal to rho cosine phi. And so this little picture right here will actually give us all of the formulas that we need to go to spherical coordinates. And so here we have our box where we'll write down all of these formulas. So first of all, again, r, I have it up here, that this is rho sine phi. So this is Cartesian plus, we'll also include like the r here, and I'll show you why this ends up being very useful. So x, right? X, if we were to put this into cylindrical coordinates, this would be r cosine theta. Now remember, in spherical, we're not allowed to have an r. We're supposed to have rhos, thetas, and phis, right? And so, however, we know how to convert r into rhos and phis. So I'm going to go ahead and just plug that in for rho sine phi cosine theta. So again, x is equal to rho sine phi cosine theta. And now we see that we've turned our Cartesian thing into something where we have all spherical parameters, right? The rho, the phi, and the theta. Likewise with y. Y is supposed to be r sine theta. And that's perfectly fine for cylindrical. However, for spherical, it doesn't have r, right? So you can't use that r there. We need to trade that in. But again, using that nice diagram that we have, we know that r is equal to rho sine phi. So rho sine phi sine theta. There we go. We know that z is equal to rho cosine phi. That was back from up here. And then finally, this one takes a little bit to show. But if you use this up here, it's not actually so bad. So let me do one step and then we'll go and look at that picture. So x squared plus y squared plus z squared. Well, x squared plus y squared, we know that's the same thing as r squared. So we have now r squared plus z squared. So r squared is exactly this. Z squared is exactly that. And when you add those together, right, you're supposed to get, according to the Pythagorean theorem, the hypotenuse squared. And so the hypotenuse in this case is rho. And so you're supposed to get rho squared. This also makes sense because, again, rho was supposed to be this three-dimensional radius, this distance that you are from the origin in 3 dimensions. And so notice that this is very similar to our original distance equation, right? Our distance equation, if you're talking about distance from the origin, would be the square root of x minus 0 squared, y minus 0 squared, z minus 0 squared, right? And so that's just distance from the origin, aka rho, and then there's no square root, and so that means it's been squared, right? So that's rho squared, the distance from the origin squared. Okay, well, now that we have these formulas, and again, we'll be using them more in class to transform like full equations and all that sort of stuff, let's just get a little practice converting a few points. So in this case, we're just going to be going from Cartesian into spherical coordinates. So I have an x, y, z ordered triplet, and I would like to figure out what is my rho, my phi, and my theta. Okay. Well, one thing that we know, right, is this last equation, right? X squared plus y squared plus z squared, that's supposed to be equal to rho squared. So let's go ahead and start off with this first one here. Let's square the x term, square the y term, square the z term, add them all together. We're supposed to get 2 here. That's supposed to be rho squared. So similarly, we're going to have just positive rhos, positive radiuses here in 3 dimensions from the origin. So this is just going to be root 2 is what I'm going to write down. Okay, well, now we have a few choices on how to proceed. I think, one way to do this is to use this z coordinate next, right? We know the z coordinate is 0. So 0 is supposed to be equal to rho cosine of phi. And better yet, we know what rho is, right? Rho is supposed to be equal to root 2. If we go ahead and divide both sides by root 2, well, we're just going to get 0 is equal to cosine of phi. And cosine of phi, well, when does that equal to 0? That's exactly when phi is equal to pi over 2. So there is that. And notice that, again, phi only ranges from 0 to pi, right? So that's none of the other solutions for when cosine is equal to 0 are in that range of 0 to pi. So again, pi over 2 means that we're looking straight out, towards the horizon sort of deal. We're not looking up, we're not looking down. And so it kind of makes sense, right? That in this case, straight out, in the XY plane here is where z is equal to 0. Okay, and then lastly, right, we need to figure out a theta value. Well, there's a couple of different ways that we can figure out a theta value. But one way is that we can say that theta value is supposed to be the exact same theta value from cylindrical. And so we can use our cylindrical equations here to help us solve for that theta value. And one of our cylindrical equations says that y divided by x should be equal to tangent of theta. And so in this case, our y is 1, our x is 1. So we're looking for a place where tangent of theta is equal to 1. And that's only going to happen when theta is equal to pi over 4. At least, in that first coordinate there. Of course, it will happen later on. But with a positive rho, this is the only place, right, that in order to get this 1, 1, 0 in 0 to 2 pi to get this to work out. So again, if I was to write down maybe rho, theta, and phi, theta, phi, we now have all of these. Rho is equal to root 2, theta is equal to pi over 4, and phi is equal to pi over 2. So this right here would be my final answer in this case. Okay, one more of these. We have 3, 4, 5, just as before. Please pause the video, try this one on your own, see how far you can get, and we'll come back and spoil the surprise. All right, so the correct answer here is rho is 5 root 2. Theta is, oh, sorry, I have these the wrong way. Other way around. Theta is tangent inverse of 4 over 3. Sadly, there's not any way to simplify this. You can't get a decimal answer. And if this was a D2L style question, you would want a decimal answer. But in WebWork, you should enter it just like this. And then finally, the phi is going to be pi over 4. There we go. Now I can highlight that, and that is the correct answer. So let's step through this and see how I got these results. So first off, just like before, we went to calculate the rho. So with rho, we took our coordinates 3, 4, and 5. We squared them all. We summed them together. That gave me 50. And then we take the square root, right? Because that's supposed to be rho squared. And then take the square root to get rho, which is root 50. You can simplify that a little bit and get 5 root 2. That becomes helpful. We next use our z equation here, right? Our z equation said that z is supposed to be equal to rho cosine of phi. So we're using this one right here. We now know what our z is. Of course, that's 5 from the statement of the problem over here. We know that rho is that 5 root 2. And then now we can use that in order to solve for phi, right? So I can divide on both sides by this 5 root 2. I rationalize my denominator here, you can see, and we get cosine of phi is equal to root 2 over 2. And we know a place, of course, on the unit circle where cosine is equal to root 2 over 2, right? And that's going to be at pi over 4. Finally, I did want to showcase that not every choice of values that you're given necessarily live on the unit circle, and so sometimes your answers do get a little bit messy, and so that's why I decided to leave this with a little bit of a messy answer here for you, right? Similar to last time, in order to solve for theta, we're going to go ahead and use an equation actually from cylindrical, which actually even that's from polar, right? And that's going to be our y value divided by our x value is equal to tangent of theta. When you try to solve for theta, right, well, there's no place on our unit circle of the nice values that we have memorized where tangent is equal to 4/3. And so if that case, right, we just need to, well, get rid of the tangent. And the way that you get rid of the tangent is by applying a tangent inverse. Now we're lucky because, right, our TI-30 calculators have tangent inverses on them, right? And so you can do tangent inverse of 4/3 in your calculator and get some decimal answer. However, again, if you're entering this into like web work or something like that, you should leave it exact. And remember, we accept the decimal answers in D2L just because it doesn't understand, right, the exact answers. But typically mathematicians really want exact answers whenever possible. So, all right. Thank you very much, guys, for watching. Again, when we talk about this in class, we're going to be talking about full-on surfaces in cylindrical and spherical, and then we're going to be talking about parametric surfaces. So, all right, take care, and I'll see you in class.